Simon Peyton Jones and Tim Harris. Hi. How you doing? So, what are we doing here? Why am I here? What are we talking about today? What are you working on? How's that?
So you're coming here to talk about transactional memory.
Yeah.
So the target area here is concurrency. Right? Everybody wants to write concurrent programs, and everybody knows that it's difficult to do, and everybody knows that it's becoming more important now that multi-core processors are becoming actual rather than merely hypothetical. So there's much more priority now on being able to write concurrent programs that work.
Mm-hmm.
And for a long time, that's been a problem that's been studied for a long time, but without a great deal of progress. So over the past 30 years, we've really stuck with the same technology for writing concurrent programs for shared memory machines, and that is locks and condition variables.
Mm-hmm.
So they were first introduced, Tony Hall called them monitors. And now they're called synchronized methods, or what are they called in C#?
Locked methods.
Locked methods.
Locked
right.
methods.
But it's really the same basic idea. And lots of research has been done to help us write concurrent programs that use this mechanism.
Mm-hmm.
But for reasons that we can go into,
Good.
Tim and I think this is a fundamentally flawed way to write concurrent programs. So my favourite analogy is it's like trying to build a skyscraper out of bananas. So very skilled builders and bricklayers can learn how to hook bananas together in ways that are reasonably stable, but it's not a very good use of their skills. And even if it was, they skilled people build these structures out of bananas, and but they tend to fall down rather easily. They're fragile. So rather than invest more research in better banana structuring mechanisms,
mm-hmm.
we'd like to just provide a better fabric out of which to build your concurrent program in the first place.
Okay.
And that's what this work is really about.
So let's talk just for a moment, though. What about like the kernel? Like kernel developers are writing living and breathing locks, right? And Windows is pretty stable. Right?
So, like I say, skilled developers can learn to do it.
Okay. So the idea is to make it easier for people to write concurrent code?
Right.
Okay.
Much easier. Yes, because at the moment it's unreasonably difficult. I can give you an example about that too in a second if you like.
Sure.
But it's unreasonably difficult. So what you end up doing is you end up obeying quite draconian rules that mean that your program is much more likely to work. And even then, there's plenty of kernel bugs that show up and then have to be eliminated.
Good point.
Yeah.
So how does software transactional memory help with this problem?
Well, in some ways it's a bit like changing from doing manual storage management in C to using an automatic garbage collector. It gets rid of a whole lot of complexity and shifts the responsibility for that complexity away from the programmer and into the runtime system. In the case of transactional memory, the complexity it shifts around is the acquisition and release of locks. Instead of the programmer having to say, I'm going to acquire this lock here, hold it for this section of code, release it again.
Mm-hmm.
The programmer marks a section of code as running atomically, meaning it runs in isolation with respect to other threads, that it either all runs or looks like none of it runs.
Okay.
And then the runtime system deals with taking locks, releasing locks, or using other kinds of concurrency control mechanism to actually get that atomicity. So it's a bit like programming with transactions in a database. The database programmer says when to start a transaction. They issue a series of SQL operations. They then say when to commit the transaction. And it's up to the database system to deal with concurrency control. We're doing really exactly the same kind of, we're building the same kind of abstraction, but at the much finer granularity of shared memory data structures inside a program, rather than access from the program to the database.
Excellent.
So here's a picture that we've often found helpful to draw, which is here's the hardware.
Okay.
And then there's some kind of abstraction over the hardware that starts off as being locks and condition variables. And on top of these, we like to build libraries in a modular way. So you'd like to build your libraries kind of like this, in nice modular stacks. So these are, and so out of this abstraction, you build more and more sophisticated abstractions until finally you get up somewhere here to your application program.
Okay.
But the trouble is that this bit here is not a good substrate. It's actually sort of more banana-shaped here. And what that means is that it's actually impossible to build modular libraries. So we can explain in a sec what we mean by modularity and why it's very difficult to do with locks and condition variables.
Cool.
And so our game is to say, let's replace this layer entirely with atomic blocks. And on top of this substrate, it turns out that it really is possible to build libraries in a modular way.
I see.
So that's it kind of makes a fundamental difference to the substrate on which you're building your programs.
Sure. So as opposed to building your house on sand, you're building it on a stable foundation.
There you go. So this is a pretty substantial claim, and we should spend a little bit of while amplifying, in some detail what we mean by that.
Absolutely. But it is interesting, the whole notion of software composability,
right.
Engineering composability. That's
what it's about. So in fact, our first paper about this was called Composable Memory Transactions, because the emphasis on composition is fundamental.
Excellent.
Yeah.
So how does it work?
Well, at the high level, what the programmer does is to mark out a section of code as atomic.
Okay.
So a very contrived example we often use to illustrate this is a program that's dealing with a set of bank accounts. It wants to credit accounts, debit accounts, and so on. And if the program starts out perhaps with an operation to credit some money to one account, so it's crediting $100 to account M, and we want to update that program to credit money to one account and to debit it from another, so doing an atomic transfer between the accounts without the intermediate state where the money's in flight being visible. That's something that's very hard to do with logs. With atomic blocks, the programmer simply needs to mark a section atomic and then have the credit and the debit operations go on inside that section between the two accounts.
Mm.
Then going down through the levels of this, from the implementation of atomic blocks down towards the hardware, what the compiler and the runtime system are responsible for doing is to ensure that each time code within the atomic block is accessing data that might be shared between multiple threads, that it makes sure that that thread that's accessing it has exclusive access to it during the execution of that block. So in this case, when modifying accounts M and N, you could think of it as automatically adding in operations to obtain exclusive access to the first account before it's accessed, and to the second account before it's accessed. And then that makes sure that if another thread is trying to work on those same accounts at the same time, that they can't both get into a jumbled mess with some of the operations going on and conflicting with some of the things that the other threads do.
Okay.
Now, there's a lot of challenges in actually getting that to run well and getting it to scale on the kind of multiprocessor hardware that we're starting to see emerging in the market at the moment. Particular concerns are making sure that if one thread is working on accounts A and B, and another thread on accounts C and D, that those are able to run in parallel, that we don't start introducing new kinds of contention into the system that aren't visible to what the programmer would be thinking about in terms of the data structures that they're manipulating. And another case is if we have lots of threads that are just reading from accounts, instead of crediting and debiting, they're looking at the balance in an account. We'd like those operations to all run at the same time, because they don't need to coordinate with each other in the same way that updates to accounts do. So those are the kind of low-level implementation worries that we've dealt with in a lot of the research work we've been looking at on transactional memory and atomic blocks.
So the semantics of this is just execute this as it were sequentially in isolation from the rest of the program.
Okay.
And when it finishes, then its effects become visible to the rest of the program.
Okay.
So can you? So I guess I'm not yet understanding just what you
Sure.
might mean by whether this thing completes. I mean, of course, if the program gets to here, your programming model is very simple. If the program gets to here, then this must have completed.
Good. Okay. I guess that's what I meant. I mean, it is sequential to me, the programmer.
So it is as if your programming model is that it is as if the atomic blocks had occurred sequentialized. They're not going to be sequentialized in reality, but your programming model, from the point of view of what is the overall transformation on memory, is as if they were serialized, and that's what makes it so much easier to reason about. Because the big thing about atomic blocks is they make the program much easier to reason about. If you have a if you're looking at the meaning of this block, you can reason about it exactly as if it was a sequential program, but you don't have to worry that some other thread is going to be messing with memory in the middle of this code, right? Because you have effectively exclusive access to memory. That's not the way it's implemented, but that's your semantic model. And so all your reasoning principles about reasoning about sequential code just work.
Excellent.
All your reasoning tools, just static analysis tools, just work.
And debugging.
And debugging.
So I put a breakpoint there. It's all occurring sequentially to me.
So if you put a breakpoint there, yeah. So actually, I'm not sure what would happen then. So probably then you'll stop. You'll see what memory is, and then when you resume, it'll probably rerun the transaction.
Okay.
Because somebody else would have messed with that memory.
Interesting. So I guess what I was kind of bumbling on about earlier was that transactions are necessarily somewhat expensive, correct? In terms of performance and processing, or is that just mythology?
Well, there's certainly overheads that the implementation introduces. So if you think about one program that has this atomic block marked in it, then that's going to run. It's not going to run as fast as the same program without the atomic block in, just doing the credit and debit directly. But exactly how much slower that runs really depends on what you're measuring against. And comparing against a sequential program without any support for concurrency control is a really hard yardstick to be measuring against. So, for example, in some benchmarks we've looked at, if you take the implementation using atomic blocks for concurrency control and compare it against an implementation using just simple locking, so the kind of locking that we teach in an undergraduate programming course, then the system using transactional memory won't run as fast as the one using locks. It might scale a lot better. If you're looking at the performance on 1 or 2 or 3 or 4 processors, transactional memory one might be slower. But if you then look at 8 processors at 16, in some cases we've looked at up to 106 processors.
Wow.
The performance of the one built on transactional memory still scales nicely.
Okay.
Whether that applies in real programs other than the small benchmarks we looked at in that particular study, that's a question that we're still investigating. But it shows the potential for transactional memory to work on systems with large numbers of processors. In other work, we've also looked at using the compiler to try to reduce the overhead of transactional memory. The Bartok system from MSR Redmond is a testbed we've looked at for that, having compiler analyses that examine the code and see that an atomic block is accessing several pieces of data that are in the same object. And in the particular implementation of transactional memory we've done in Bartok, that enables the compiler to eliminate some of the concurrency control on the second access, the third access, and so on to that same object. So we're really just at the start of looking at that whole area of compiler analyses and optimizations. So I think as with, say, the emergence of object-oriented programming in the last few decades, there's a whole line of hopefully fruitful work to be done on optimizing for the kinds of performance, the kinds of usage that are seen in real programs.
Excellent.
So a short summary would be, the programming model is just way easier. The implementation model, the measurements we've already done, and the implementations particularly Tim and his colleagues have already done, show that the overheads can be, at worst, a kind of a factor of 2 or something, but much more typically like 5% or something more like that. So
5% is very,
right.
very optimistic.
All right, but so but there's some kind of, at some level, if you want your program to work at all, right, you might be prepared to pay, particularly in this area of multi-cores, you might be prepared to pay a relatively small performance thing. But and the other thing is, as Tim says, we've only just started trying to improve the performance. If we throw a few hundred PhD students into the trenches, then by stamping on their sort of prone bodies, we'll build a wall that enables us to go a lot faster. I think of virtual memory. Right. Initially, it seemed unreasonably expensive. With a bit of hardware support and operating system support and software support, its benefits far outweighed its costs in practice. And it's that kind of abstraction It pushes a whole lot of complexity in exchange for very simple top-level abstraction.
Excellent. Now, I just recently interviewed Jim Laris et al., Singularity people. Have you been doing any work with them in testing this out in an operating system environment?
We've just started doing some work like that.
Okay.
And the Bartok system that I just mentioned is actually the compiler that the Singularity project uses.
Yeah.
And so one of the goals of prototyping transactional memory has then been to make it available to all of the people working on the Singularity OS. Because the operating system kernel clearly provides an environment which has got to handle concurrency because it's running on multiple processors controlling resources on the machine. But Singularity also provides a particularly interesting setting because its programming model takes what would be a monolithic application on Microsoft Windows and decomposes it into large numbers of communicating separate processes with concurrency within those processes. So it's perhaps more likely that there'll be a large number of threads running in a Singularity system than there would be in a traditional one. And also because it's a system where we're really starting from scratch and looking at structure of operating systems and structure of code, it provides a good chance to look at modern ideas for concurrency control and for system structure without having to consider all of the legacy and migration issues that we'd have to look at in existing environments.
Excellent. So how do you play with this stuff today? So what languages are you using? I know I've seen this.
So one place we prototyped this stuff was in Haskell. Haskell's a purely functional programming language.
Okay.
With support for very lightweight concurrency. It's also a strongly typed language. And it also has, very crucially for this work, it has a distinction between pure computations which have no effect and side effecting computations which may have side effects on mutable variables. So this is really good for transactions because in a transaction, a particular function might have a lot of effects on memory which are pure. So a function which, say, just adds up the numbers between 1 and 100 but has no effect on mutable variables may do a lot of reads and writes to memory, but they don't need to be tracked by the atomic memory transactional system because they're invisible to any other thread. The only things that are visible to other threads are mutations of shared mutable state, and in Haskell programs those are identified by their type. So what that means is that this made it a particularly friendly environment for implementing transactional memory because it means that we can track just the operations that are potentially visible to other threads, and they are a tiny minority of all memory operations.
Excellent.
So that made it a good context in which to try this out. So you can download a version of our Haskell compiler. It's called GHC. It's readily available from haskell.org, and you can try out transactional memory using that.
Excellent.
But also, Tim and his colleagues have implemented this as a library in C#, which is a bit clumsy to use, but nevertheless implements the basic concepts, and also in a more deep integration in the Bartok compiler. Also for, well, that's for any MSIL generating compiler, in effect, so that would be C# and Visual Basic and all the rest.
Excellent.
But those, the Bartok implementation is probably not available outside Microsoft, is it?
That one isn't at the moment. The library-based implementation is available from the Cambridge Download site. And that was work that Maurice Hurley from Vann University did on sabbatical here last year. I think it's on his own pages at Vann as well. And that lets you experiment with this kind of basic form of atomic block in C# code without a great deal of complexity. The program needs to follow certain guidelines about how it accesses shared data.
Okay.
I think it needs to use property accessors rather than directly accessing fields of a shared object. And that lets the system that Maurice worked on insert its own hooks to track those accesses and to make sure that it does the concurrency control correctly.
Excellent. So you hear that, Niners? Play with it. Excuse me.
Right. At the beginning we talked, made all these claims about how this is that locks and condition variables don't support modular programming.
Yes.
And atomic blocks do, but we haven't really substantiated
Let's rock and roll
yet. So
okay.
we could do that a little bit.
Please.
So why are locks and condition variables modular? Well, so this example we got on the board already shows part of it. Supposing I do this game without atomic, but with lock. So what does that mean? So inside credit, I'll use a locked method. So what that means is that the credit method is going to, under the control of a lock, it's going to read the variable containing the balance, add something to it, and then write the variable controlling the balance. And because it takes a lock protecting the M object, it's going to do that indivisibly. Nobody else is going to be able to get in the way.
Okay.
But if I combine it now with this guy, so I'll credit $100 to M, and then I'll debit $100 from N, and both of those will be indivisible. But the pair together, there will be a point in the middle at which an observer could see the money in neither place. Or perhaps in this case he'd see
Both places.
Both places, yes. So he'd see $100 in both accounts. So supposing the whole point was we wanted to make the intermediate state invisible to anybody else. That is, anybody looking at the state of the world would never see extra money. How could we do that with locks? Well, we have to break the abstraction. We have to say, take a lock on M. So we have to, instead of this, we're going to have to say, somehow, lock M, and then we have to unlock at the end, right?
Yes.
And now we have to worry about some other things. So for a start, we've had to break the abstraction. We had a perfectly well-working credit method, but now it didn't work anymore. We had to look inside the abstraction, see how it worked, and take appropriate locks. Maybe credit took several locks. Who knows? That's part of its implementation. If it took several locks, we probably had to take them all here. So the other worry is, we must take these in the right order. Otherwise, somebody else who's transferring money in the other direction, if he goes lock N, lock M, now we're going to be in trouble because we could get deadlock. And this deadlock was introduced, but it was introduced essentially as an artifact of the very mechanism we were using for concurrency control. It wasn't part of the original problem, which just said transfer money in one direction and transfer money in the other direction. It was a deadlock introduced by the locking mechanism itself. So what do you have to do? You have to put a global order on locks, and you have to have some kind of condition, some kind of test that says, if M is bigger than N, then lock them this way round, otherwise lock them that way round. And that's hard to get right in a big system.
Yes.
So all this means that it's not very modular. So now, what else if you want? What if you wanted to say, oh, supposing credit should or let's say debit should block if there's not enough money in the account, right? So I credit some to N, and then I debit from N. But if N didn't have enough money, I want to block, right, and just not proceed. But I don't want to stop. I don't want to block in a state in which M has the money, right? So how can I do that? Oh, I have to somehow wait here. Somehow I have to put something that says wait until N has enough.
Yeah.
Right?
Yep.
So that's tricky to get right, because now I have to look inside the debit abstraction and figure out what condition will make it run without blocking, without getting stuck, right? So that's all hard to get right. Let's contrast what you might do using atomic blocks. You do this. Let's go back to the second atomic.
Excellent.
That's all, right? So inside credit, we had a working credit method, and it continues to be a working credit method. We wanted to call other atomic functions in here. That's fine too. And the atomic just guarantees that it works indivisibly. What about this blocking mechanism I was describing? So we haven't discussed that at all.
No, we haven't.
But this was one of the main insights we had when Tim and I started to work together. It's probably a lot of this, we should say, was invented by other people. Right, years ago, the database people invented transactions. Maurice Herlihy in '93 suggested applying transactions to in-memory operations. So a lot of this is kind of not our work at all. But this retry thing probably is. So how do we write debit if we want to block? So here's how we write debit. Debit N is going to, so there's going to be some kind of integer, there's the balance. So, and what we're basically going to do is we're going to say balance is balance minus N. That's what debit is going to do. But it's got to stop if there isn't enough money in the account. So we're going to say if N is, let's get this right, N is bigger than balance, then, so I'm going to put this in red because it's the new part, retry. So what does retry mean?
Yeah.
Retry means go back to the beginning of the enclosing transaction, that is this one, not the beginning of the method, the beginning of the atomic block, inside which, perhaps at many levels of function call, inside which this function is being called, go back to the beginning and rerun it. That's the semantics. So, of course, if we went back to the beginning of the transaction and reran it right away, we'd simply end up in this retry again. So it would be like busy waiting.
Understood, but
Right.
I mean, the thing though, the retry runs the entire transaction
The
again,
entire transaction again.
even if you only wanted one method in it to run again. Which, I
Yes.
mean, that's the whole idea of atomicity, right?
Yeah.
I mean,
And it's very important that it runs the whole transaction again, because when it goes back to the beginning here, remember it's going to discard any intervening effects, so that M has not been credited with 100 now. And indeed, maybe it shouldn't be, because perhaps this was in an if that said, if something or other, then credit M with 100, else may credit somebody else, perhaps, right?
Excellent.
So by the time N does get enough money, the control path that got to crediting M might not be the one that should be taken, right?
yep.
So the semantics is retry goes back to the beginning of the transaction and runs it from the start.
Okay.
So you might worry about efficiency. Is this like busy waiting? Well, so when might it be sensible to retry, to rerun it? It might be sensible to rerun it when any variable read during this transaction has been written by some other transaction. So the read set of this transaction intersects the write set of some other transaction.
Okay.
Right? So the substrate, the runtime system, arranges that when you call retry, it doesn't immediately retry it. It blocks the thread until the read set of this transaction intersects the write set of some other transaction.
So if you have a shared bank account with someone,
Yep.
and you're both doing these operations at the same time,
Yep.
you handle all of the possible problems and collisions.
There you go.
As it were.
There you go.
Excellent.
So this is key to modularity, because you notice that debit now has this retry in it, and it can be called in an arbitrary nested way. I could debit somebody else's account as well. If I had p.debit 50, maybe I'll do a 50 here.
You see?
So now there are two ways in which you can block. We can block because N doesn't have $50, and we can block because P doesn't have $50. But the programmer doesn't have to know that and doesn't have to pull some condition out to the front. The system will automatically just block. It will only run to completion if they both have 50. If either doesn't, we'll retry that.
And there's another way that atomic blocks help composability as well, and that's that, you know, let's suppose the bank here is more like my bank, and rather than having me wait if I don't have enough money to pay a cheque, they'll send an exception. They won't allow that transfer to go through. Then we could write that using transactions by saying if we're trying to do too much, then throw some kind of exception.
Okay.
And let's say we have the atomic block still crediting M, and then trying to do the debit afterwards. If we get an exception coming out of this, then because of atomicity, we roll back the updates that the atomic block has done before throwing the exception onto the code outside the transaction. So that gets rid of the need to write all kinds of fix-up code. I don't have to try to debit the account. Do I get an exception? If so, then debit the money back out of M. But maybe someone's taken the money out of M in the meantime and got all these kind of error recovery cases to deal with.
Okay.
Right.
And that kind of code is very difficult to write and to test because it's so rarely executed in practice. So by being able to deal with exceptions and get the same kind of failure atomicity benefits the database programs do, we hope we avoid another class of error that can come up in concurrent code.
Excellent. But let's talk about that for a second. What happens when an exception occurs inside the atomic block?
So we've actually explored a number of different options here, and you know, we do need experience using these in real programs to get a good feel for what makes sense. But at the moment, our intuition is that if an exception is raised anywhere inside this atomic block, then there are really two cases. One is where the code inside the transaction is able to handle the exception. So I've got atomic here, then I enter a try catch, and an exception comes out in the middle of it. I maybe want to handle that exception and try something else still inside that transaction, not rolling back what's happened so far.
Okay.
Another case is where the transaction actually escapes to the edge of the atomic block. And what we do there in the Haskell prototype is to roll back all of the updates that the transaction has made, and then to raise the exception again. So an exception can be used as some kind of error signalling mechanism that says something has gone wrong, and we then use the transactional memory mechanisms to put the system back into a consistent state. If you think of each successful transaction as moving the system from one consistent state to another, then it's only those transactions that complete without raising exceptions that whose effects are retained. Everything else is rolled back, hopefully getting back to a consistent point.
Hopefully.
So when you look at this code,
Yeah.
if m.debit raises an exception, your programmer can look at this code and say, m will not be credited. Right?
Sure.
And that's a very valuable thing to be able to say. If you look at this code in a locking situation, right, and say, could you guarantee that if n.debit raised an exception that m wouldn't be credited? Absolutely not.
No.
You would have to catch the exception around this n.debit and remove the credit from m. Here there's a structural guarantee that only if the program counter exits at this endpoint here, right, will the effects be committed. That's an incredibly strong guarantee to be able to make.
Absolutely. So is there a way for multiple transactions to communicate?
In the Haskell prototype, we only let transactions communicate by committing their updates to the heap.
Okay.
So that fits with the basic ideas of serializability in database transactions, that you can take the transactional code and it'll look like it runs in one sequential order or in the other one. I know in databases people have looked at other forms of communication between transactions and forms of nesting between transactions, but one of the big appeals of atomic blocks in a programming language is just being able to think of them as sequential updates to a single shared heap, and so going beyond that maybe adds some complexity to the thought processes of programmers using it, and so we need to explore carefully whether it is desirable adding other kinds of communication.
Sure. Now, is there any implications for this with the garbage collector?
Oh,
I mean,
so sure, in the implementation, the garbage collector needs to know what's going on. So as Tim described, there are lots of... One of the nice things about transactional memory is that it's a simple abstraction with a variety of rather subtle implementations.
okay.
That's a good property. A good abstraction has that property. It has a simple interface, but it may be tricky to implement. So this one is a very simple interface. Atomic, retry, or else, which we haven't talked about, and
We
mutation.
should.
That's it.
Wow.
So its programming interface is extremely simple. So the variety of implementations, all of which are going to catch some kind of logging information as you go along. Right? As you need to keep track of which variables, which locations have been mutated in some form or another. If garbage collection strikes in the middle of that transaction, then if the garbage collector is going to move objects around, it had better move the pointers that are held in this log. So the garbage collector needs to be cognizant of the implementation of the transactional memory. Yes.
Interesting. So does that mean that the garbage collector will need to be rewritten or just made... I mean, how do you make it aware of the existence of this? Let's say that we can get this running on a system today, as you mentioned, the C# sample.
So in the Bartok prototype and in Haskell as well, the implementation of transactions is done as part of the virtual machine. So it's implemented kind of alongside the garbage collection with a knowledge of how the collector works when it runs and so on. So one example is if we think about a program that starts off by having, let's say, variable x refers to some object, and we then enter an atomic block and make a tentative update to x, we allocate a different object and assign it to that same variable. And then if the garbage collector runs at this point, it needs to know that there are these basically two different versions of the world, at least as far as this one thread is concerned. We don't yet know if this atomic block will run to completion or whether it's about to raise an exception. So the garbage collector needs to know that this object here is still potentially going to be used by the program, and also that this new object here is potentially going to be used. So we deal with that simply by extending the set of objects that the garbage collector knows about, treats as part of its root set in GC terminology, to include the values being overwritten in the atomic block, as well as the actual values tentatively in the heap at that point.
Excellent.
Then we can do some improvements on that as well. A very contrived example would have three objects, let's say x, there, another assignment to x, and then a third assignment of another variable, another value to x. If the GC runs here, then it knows that this first version might be needed if the atomic block rolls back. it knows that this last version is going to be needed if the atomic block commits, but it doesn't actually have to keep this intermediate version anymore, because that's been overwritten. It can't be used whether the transaction commits or whether it aborts. So some of the techniques we looked at in the Bartok system are exploiting cases like this to try to trim down the amount of data that the transactional memory system retains, just to include the things needed on rollback and the things needed on commit, rather than all of this kind of intermediate data that actually is genuinely garbage and can safely be collected no matter what the future path the execution takes is.
Excellent.
But the short version, to answer your question about do you need to change the implementation of the garbage collector, is for almost all of the garbage collector, no. What you need to change is the root set enumeration for a thread, because every thread now carries a log with it when it's inside a transaction, and the root set enumeration for a thread must now traverse the log, perhaps in a somewhat intelligent way, as Tim said. So there's just one point in the garbage collector which you need to futz, really, and that's finding the pointers that are in the log.
So let's talk about the asynchronous side of this. So I could have several asynchronous operations inside my atomic, which does make it a little more complex, doesn't it? Because you guys aren't necessarily going to know when the operation completes. Let's talk about that for a second. Asynchronicity inside of an atomic block.
So
does the question make any sense, or is it one of my usual ones?
And we try to distinguish between what we call concurrency and what we call parallelism.
Okay.
Where concurrency means having work going on at the same time, because it really needs to interact with different external things. One thread interacting with a user, another fetching blocks off disk, another issuing RPC calls over the network. And so in those cases, we really need those things to be running, or considered for running at the same time, so that the system makes good progress. And then parallelism is the second case you talked about, where we're wanting separate tasks so that we can make good use of the hardware resources that the machine has.
Yes.
And the way that I see atomic blocks being used is really in kind of the communication between concurrent tasks. That it's where perhaps we have different threads interacting with different clients, then wanting to put the results together, maybe to put work items on a work queue, manipulate some kind of data structure in shared memory. And that when dealing with parallelism, where we're looking at trying to get lots of work to keep different processes busy, then perhaps that makes more sense to implement using different constructs from atomic blocks. And we've started looking, and Simon's been looking in the case of Haskell, at constructs for data parallelism, for expressing operations that can be performed in aggregate over all of the elements in an array or a matrix. And that kind of more structured way is perhaps a good substrate for building highly parallel systems, because it can scale across wide numbers of different numbers of processors. Hopefully we can continue finding work for extra processors to do as it goes beyond the 4-way, 8-way kind of systems that we see in the nearer term.
Excellent.
So nevertheless, I think that this whole transactional memory idea is a coordination mechanism for shared memory concurrency or parallelism. So the same territory as condition variables and locks are used for at the moment. And just as condition variables and locks are used at the moment for the kind of asynchronous parallelism or concurrency that Tim was describing, and also for coordinating threads in a shared memory multiprocessor, so transactional memory can be used for both of those things. The place where I think it's much less applicable is when you want to talk about distributed memory machines, in which there's different address spaces with long latency, relatively low bandwidth pipes connecting the different address spaces, and perhaps possibilities of failure and authentication across. So there I think you really need a different concurrency abstraction mechanism altogether.
Excellent.
So for the shared memory case, so I think that for relatively the modest numbers of processors that we see in the near future, I think it's that transactional memory is a much better replacement for the locks and condition variables that we are otherwise going to be using. And to answer your particular question, for asynchronous programming, when you're trying to program UIs, transactional memory is just what you want.
It is.
Absolutely.
Okay.
Yes, it's exactly what you want. But you had a kind of particular query to do with it. Your first reaction was it wouldn't at all be what you want. So perhaps we should just explore a bit why you thought that.
Sure.
And we could figure it out.
Excellent.
Because we think it's exactly what you want for that particular.
Well, because the only reason I said that was if I have inside of an atomic block, I'm doing, 10 asynchronous operations, like I'm spawning new threads to do things for me. One of them might be long running, and then I guess my point is it's still complicated for me as a programmer when exceptions happen in an asynchronous thread. So it's still going to be a strange world for what you guys are doing in the atomic block. But of course, this is based mostly on my misunderstanding. I mean, I'm just learning this as we're going along here. So, is there anything to my thinking in terms of the complexity for what you guys are doing in terms of if I write highly parallel code inside an atomic block, or is that what you expect people to do anyway?
So wait a minute. Several things to say here. Firstly, this is not a silver bullet. Right? Concurrent programs are difficult to write and will stay difficult to write. It's like, so moving to transactional memory is like moving to a high-level programming language from assembly code.
Okay.
Right? You can still write buggy programs in C#, even though it's not assembly program. It's just that the bugs are more interesting, and the whole class of bugs is eliminated by moving to a higher level. So you will still be able to write programs, concurrent programs, with concurrency bugs in them, absolutely. So that's the first thing to say. It doesn't make concurrency easy, unfortunately. Second thing to say is, within an atomic block, can you spawn new threads? Right, so this is our baseline position is no, right? Okay. For the following reason, that an atomic block is meant to do an atomic effect on memory. Read a bunch of locations, write a bunch of locations, right? If it's very, very long, if it takes a long time to do that, then the chances are big, and if it touches a lot of memory locations, the chances are that some other transaction is going to come along and screw with some of the memory locations that this big long-running transaction is going to do. So when the long-running transaction gets to the end, it's going to say, oh my goodness, somebody's messed with my memory, so I better start again. Right? So a long-running transaction is typically going to be bumped, right, and may continually rerun. Now, if your transaction is long enough that you're thinking, oh, to gain performance within this single transaction, I'm going to spawn zillions of threads and then join up their results, the chances are you've got too big a transaction anyway.
Okay.
So in the asynchronous kind of applications that you were describing, the kind of situation is that you might spawn, let's take an extreme example, you might spawn a thread for every button in your UI. And the purpose of that thread is to listen to that button and then to send a message through a transactional data structure to something that's going to cause some effect. Now, that little thread isn't going to do much parallelism, right? Its whole business in life is to listen to that button, do a little atomic transaction, and then go and listen to the button again. Right? So the whole game of asynchronous concurrency is not to write event loop kind of code, but instead to spawn lots of threads, most of which are blocked at any moment.
Okay. Interesting.
Did that help?
That did help, absolutely. So I'm not quite certain I completely understand how what you're doing applies to the explicitly to the multiple core scenario, the multiple processors. I mean, let's talk about that for a moment. So I guess that's my question. Can we dig a little bit more into that? So,
and there's nothing really that we're doing that specifically requires multi-core computers. And a lot of this is work we've investigated for some time on SMP machines, on existing shared memory architectures. So I think there were really two key things that maybe multi-core introduces into this area.
Okay.
One is simply the increasing ubiquity of hardware support for parallelism. That it makes it much more important to be able to write software that will make good use of multiprocessor hardware, and so that puts a new emphasis on programming techniques and languages that favour developing for those systems. And the other is that as we see new multi-core processors coming up, there's so much discussion about new kind of hardware features, new kinds of communication mechanisms between those cores, that perhaps we can get down some of the overheads that have existed in these systems on older multiprocessors. We've traditionally had a mental model about what it costs to do an atomic memory update to shared memory, what it costs to get a cache line in exclusive mode from one processor to another. So as those variables change, the kinds of implementation techniques we can use effectively will change.
Excellent. So I heard the mention of something called or else.
Oh, right. So this is back to modularity.
Sure.
So let's go back to our bank account example yet again. And so now we want to credit M with $100, and then we'd like to take that $100 either from N1 or from N2. Right? If N1 has enough money, we'll take it from him, and if N2 doesn't have enough, if N1 doesn't have enough money, we'll take it from N2.
Okay.
So how can we do that? We can say, and we'd like to do that without futzing with the implementation of debit, right? So we don't want to first look inside N1 and see has he got enough money, because that breaks the abstraction. So we'd like to say N1.debit 100, or else, maybe I should write it like this: do N1.debit 100, or else N2.debit 100. So this or else construct is the other main construct that we introduced. So we've got atomic, retry, and or else. Those are the three main combinators here. And so what's the semantics of this do or else construct? It says, well, run this debit thing, and if it retries, right, this guy, if he calls this retry up here, right, then run this branch, run the else branch. If N1.debit succeeds without calling retry, then the or else part is not run at all. Right? We just proceed out here. This is all in an atomic. Right? So this is anywhere in an atomic you can do this do or else thing.
Okay.
So we credited N, then we try to debit N1 by $100, and then we try to debit N2 by $100. And we'll only try the N2 if the N1 fails. If they both fail, that is, they both retry, that means neither of them has $100. So what should happen then?
Roll back.
Then the whole thing retries, the whole do or else retries, because it, after all, might be in another do or else, a larger do or else construct, right?
Okay.
So eventually, all of the do or else's will have retried, and then we go right back to the beginning of the atomic under the semantics of retry and just rerun. Right, but now the runtime system knows that we read M, we read the contents of M, we read the contents of N1, and we read the contents of N2. So it will know to rerun the transaction whenever N1 or N2 changes. So in this modular way, without having to pull out the condition that says rerun if N1 or N2 get more money, that kind of automatically comes out in the wash. Right. So it's kind of modular choice. Now, in operating system settings, there are system calls often for being able to wait on multiple I/O handles at the same time. In Windows, it's called
wait any.
Wait any. That's right. You wait on an array of handles. In Unix, it's called select. But what that means is, if you have a procedure that calls wait any, and then another procedure that also calls wait any on a different pair of handles, how could you wait on either of those two procedures to be ready? You can't do a wait any on procedure 1 or procedure 2, but you can only do a wait any on handles. So you have to somehow gather up all the handles that any part of your system might want to wait for and do one big wait any at the top. So the structure of your program turns inside out. But then you gather them all up, you wait on them all, and then you have to dispatch back to a kind of event handler to say what to do if handle number 73 is ready. So here you can just say call procedure 1 or else call procedure 2. Right? If procedure 1 itself is waiting for more than one channel to be ready, or procedure 2 is waiting for more than one channel, this do or else thing nests perfectly well. Excellent. So the structure of your program doesn't get turned inside out. It's back to modularity again.
Excellent.
We do actually support other uses of atomic, though, where we could mark an individual function call as atomic in Haskell. So we could say, let's bind X to atomic credit N with 100. And perhaps credit is a method that returns the new balance, or in a less contrived example in the bank account one, it would do that. Now this example does actually illustrate an important design choice that we've made in the Haskell system, and that's to actually keep the the state that's manipulated through transactions and the state that's held in the rest of the program's data structures is very separate, so that you can't accidentally manipulate transactional state without being inside an atomic block. So this kind of usage is actually fairly common, where you want to do one operation and it's a transactional one, then we have to put it inside an atomic block to make sure that it's compiled with the right transactional machinery at runtime to coordinate with other threads that might be accessing that bank account through STM.
Okay.
Right, because it's very important to make these static guarantees. If I have this debit method, doesn't in and of itself, it now no longer says locked or anything. So we'd like to statically guarantee that since debit is assuming that it's going to be called in an atomic context, you'd like to statically check that it really is. That happens very smoothly in the Haskell context. Then there's no reason it couldn't be made to happen in a more mainstream object-oriented language as well. You'd need to say something like, this debit transaction should be called in an atomic context. This means that whenever debit is called, it had better be in an atomic block or in a method which is itself marked atomic. Do you see what I mean?
I do.
Because you definitely don't want to allow programmers to accidentally call methods that should be called in an atomic context, because that's their internal assumption, and have it called outside. So there's a bit of static checking that you'd like to do, but that's very well understood technology. We know how to do that.
Okay.
That's not technically difficult. Just backing up to your precise original question, what's the programming? When the programmer sees this code, he has the following guarantee, that when this atomic block can finish in only one of two ways. Either it can be as if it had run normally, and then execution emerges here, this code having executed, or else it throws an exception, in which case none of this code is run, and the exception is raised, as it were, just at the beginning of it. Right?
Okay.
So that's a very simple programming model. It either all runs or none of it runs. And if none of it runs, the only way that could have happened is by an exception propagating out.
True. And of course, some programmers out there will just wrap a try-catch around the whole thing, right?
That's fine. That's very legitimate.
Try, atomic, catch, some exception that gets thrown from some of the code inside of it that you know about.
Right.
Move on. Don't worry about it. Do some logic and just continue on if you can. Very interesting. So, what are some other things that you want to get out there to developers about? Because it would be nice to get people to actually start using this, right, and give you feedback. What are some of the key points that need to be driven home?
Well, I'm thinking about the Haskell and Bartok prototypes. One thing that I think is important is to get some idea about the situations where atomic blocks are likely to perform well. And the situations where they're not likely to perform well. We try to design the system so that that's fairly simple guidelines to give to programmers. That if two atomic blocks are accessing data, then they can run in parallel without any conflicts, as long as the locations they're writing to don't overlap, and as long as the locations that one is writing to don't overlap with the locations that another's reading from.
Sure.
And that's really the key consideration the programmer needs to design a system so it scales well and performs without frequent re-execution of atomic blocks. But aside from that, we're really interested in seeing how programmers pick up these kind of ideas and use them in practice. Our optimization work on the system has been based on limited cases we've been able to look at in our own work in Haskell, and we may well be looking at the wrong kind of cases. There may well be new ways that programmers, new idiomatic ways that programmers use these facilities that would guide future work on optimizations.
Excellent.
I suppose my sort of top-level summary would be, we think that the whole atomic block game is a quantum step forward, not invented by us, but a quantum step forward from the blocks and condition variables story. And we tried to explain, I guess in this interview, but also there's several papers about this, some principled reasons why we think it's a quantum step forward in terms of composability and so forth. And we've also given some reasons to believe that the performance of an atomic block mechanism is or can be made acceptable. But both of these are open to questions, right? We're researchers and we haven't built big applications. So it would be very interesting to us to hear from people who'd started to use atomic blocks to build larger applications, to say, are they as more modularly expressive as we claim?
Mm-hmm.
And are the performance overheads based on the prototype implementations we have at the moment acceptable?
Okay.
So the latter, we're more confident that can be fixed in time because our prototypes are indeed prototypical. But if there's serious questions about the expressiveness, that would be really something nice to know about early.
Excellent.
So in effect, we're making claims that we have given some reason to substantiate, but truthfully, the only proof of the pudding is in the eating. So we'd like people to try it out and tell us.
Excellent, and it's easy to get a hold of, right?
So they can try it out in a very fully fledged way in Haskell, a medium in which it's very well worked out, but is somewhat unfamiliar to many programmers.
Okay.
Or they can, I guess, through the Morris's library, they can try it out in a somewhat more clunky way for C#.
Right. The SXM library supports atomic updates and retry and all else.
Mm-hmm.
It doesn't have quite all the static guarantees that Haskell can give, so the programmer has to be careful not to do real I/O operations inside a transaction. But it provides a test bed for basic shared memory updates and for building scalable shared memory data structures.
Interesting.
But even outside of trying it out for actually writing programs, I think that we'd get lots of interesting feedback from developers who read some of the papers about this, a couple of which are very readily accessible, I think, like composable memory transactions. And then just mapping those ideas, that new set of ideas, onto the kinds of applications that they are deeply familiar with. They might say, oh, yes, that would be fantastic. Or, on the other hand, I can't see how I could write my application using this stuff. Both of those would be interesting bits of feedback for us to know about.
Fantastic. And they can get in touch with you via your email on your descriptions of your work?
Yes, I think all of these papers will be on our websites at Microsoft and Cambridge. And
we'll put these links on Channel 9.
Great.
Fantastic. Well, I know I've learned a little bit here. I mean, I've learned a lot. It makes a lot more sense to me now. Thank you for your time. An hour of researcher's time is very valuable.
Great.
This is great stuff, and it looks like it's going to help with the whole composability of software, which is what we're driving for with this whole managed revolution and everything else we're doing.
Right.
Right?
Well, we're all excited about it, as you can tell.
Excellent. Well, thank you, guys.
Thank you.